would provide with a brief introduction of the Society of Petroleum Engineers and our speaker, and then the lecture starts. There will be time for questions during the question and answer session at the end of the lecture. So later, if you have any questions, you can unmute your mic or you can submit the questions through the chat box. Also, the entire lecture will be recorded and will be available on our channel on YouTube. As you are aware, this lecture is organized by AUIS SPE Student Chapter. SPE is the largest individual member organization serving manager, engineers, and other professionals in the upstream segment of oil and gas industry. So as AUIS SPE, our mission is to raise the standards of AUIS engineering students by fulfilling the SPE's international mission. Without further delay, I would like to introduce our speaker today, Dr. Abdelaziz. Dr. Abdelaziz is a professor of petroleum engineering at the American University in Cairo. He has more than 24 years of experience within different academic institutions and oil and gas industry in chemical and petroleum engineering as well. Prior to joining AUC, he was a professor of energy engineering at the American University of Iraq Slimani. Dr. Abdelaziz worked with different academic institutions as was founder of different academic departments, research centers, and a business incubator. He has authored 91 publications, including journal articles, book chapters in the areas of flow through porous media, hydrocarbon reservoir engineering, and conventional and shale gas. He has managed drilling and non-aqueous phase, liquid transport, two-phase flow modeling and simulation, and water and environmental research. Also, he's a very active member of SPE and many other technical societies at regional and international level. Well, Dr. Abdelaziz, thank you as well for sharing your knowledge with us. Without any further delay, I'm happy to turn the presentation over to you. Please go ahead and thank you.
Thank you so much, Ms. Berger, for this nice introduction. And hello, everyone. It's a pleasure again to be with you guys in Suli. I really missed you a lot, and hopefully you're going to benefit from today's lecture. And thanks for Sardam for the invite and follow-up as well. So today, as you see from the title, we're going to talk about underbalanced drilling, as mentioned by Ms. Berger, and which is a hostile friend of formation damage. Why this title? You definitely will learn as we go through the lecture how formation damage works with underbalanced drilling. Now, by the end of this topic, basically you will learn different things, whether related to drilling technology, related to formation damage, and we will see the benefits of underbalanced drilling. What type of values are added to underbalance, to the reservoir when we drill underbalance. So I tried to make the lecture informative. I did not dig deep into the details because of the mixed type of audience. So at least we can reach the outcomes of today's talk. I know that AUIS does not have petroleum engineering program, so we should not deal with details when we talk about a lecture similar to this. Well, the question that might be asked by some participant here, why should we drill? Can we avoid drilling, or if there is any way to produce without drilling? Definitely the answer is no. There is no way to produce oil and gas unless we drill. Exploration usually done by geoscientists leads to a fact that geoscientists tell drillers where to drill. Then the only way to find whether we have oil and gas in the reservoir is by drilling. And of course, drilling has developed since 18th century, and lots of technology development took place. And it was stated that if a proper technology is utilized, the production can be increased by 6-fold. Imagine nowadays the world is producing almost 100 million barrels a day, and after 10 or 20 years, the production will be 600 millions. And nowadays we have problems with the market, and imagine if the number is sixfold or increased by 6 times. Now, when it comes back to drilling, we have to differentiate between 2 types of drilling. The conventional one, which is carried over balance, and a new type of drilling, which is the controlled pressure drilling. So now when we say overbalance or underbalance, what do we mean by each of them? So when we say eventually overbalance, usually for those who don't know how the drilling process is carried out, basically we have a drill string, pipes, it's large number of pipes, and at the bottom we have the drill bit, and the drill bit is rotated by rotary table or other means, and a liquid called mud is injected inside the pipes to lift the cutting from the basically penetrated formation, and at the end from the reservoir where we have our oil and gas. Now, the overbalanced drilling, it means the hydrostatic pressure, as you learned in fluid mechanics, along with basically friction and choke pressure, is larger than the reservoir pressure. And this is usually followed for basically a safety reason. As you can see, guys, when the drill bit basically hits the reservoir here, or the top of the reservoir, no fluid is produced because the hydrostatic pressure is much larger than the reservoir pressure, and the reservoir is shown here. We have gas, water, and at the bottom we have gas, oil, at the bottom we have water. But if you look at the red area in here, basically this is the laid out mud cake. And as we go deeper, the mud cake basically is not very deep, but at the bottom or at the top of the reservoir, the mud cake is penetrated further. Now, when we need to pull out of the hole, you can see differential sticking, where the drilling string, because of the overbalance, does not go out. It sticks against the wall. So now by overbalance, guys, the formation damage is significant, especially at the top part of the reservoir, and there will be some drilling problem associated with the process, and definitely this will result in rig time losses, where lots of money has to be paid by, let's say, operating companies to a drilling company because of these reasons. The same phenomenon actually takes place in horizontal wells. And if you look at this in here, the circulation pressure, which means the overbalance pressure, is 2800 Pascal per square inch, while the formation pressure is 2200. So the overbalance is almost 600 PSI. In horizontal wells, the same phenomenon is again observed. The red arrows in here show the drilling mud direction inside the drilling string, while in the analysis, the yellow area, basically we have the returning mud returns to the surface. Again, all around the drilling string, we can see in the formation the depth of invasion or the depth of formation damage, which is basically in the horizontal well higher next to the heel, and where the toe basically, the toe damage is really minimized. So invasion process is a continuous process, although if the drilling process does stop, and a fluid solid invasion into the porous media, which is our reservoir, regardless whether it's a classic or carbonate reservoir, are usually dramatic. And of course, this results in the so-called formation damage. We damage our formation because of our actions. Okay, we force the solids that come with the mud to penetrate the porous media and damage it. What's the definition of formation damage? What is it? Basically, formation damage is a process causing a reduction in injectivity or productivity of the well. So in here, two things, because the fluid can go into both directions, either be produced or injected in case of enhancing or recovery. So formation damage eventually results both these phenomena. So other definition for formation damage by the godfather of formation damage, Brian Pinion, in 1999, he defined formation damage actually in a very nice way. And what he said, formation damage is nothing but the impairment, which means the damage of the invisible, of something that we don't see, by the inevitable and uncontrollable, something that we cannot avoid and we cannot control. No one can go down to the wellbore and control eventually the damage. This resulting in an indeterminate reduction. It will reduce actually something that we cannot determine. Also, it's there at the bottom hole, reduction of the unquantifiable, reduction of the oil and gas that we did not quantify yet. So this is very nice, actually, definition of formation damage. It's 100% true, and it did trigger actually all aspects of oil and gas production. And many people now rely on this definition when it comes to formation damage. Now, as engineers, we always love to deal with numbers. So the main equation that is utilized in reservoir engineering and production engineering is called Darcy's equations. And that has some variables controlled by nature. We cannot change them. As you can see in this equation, in the left-hand side, we have a Q that stands for oil flow rate. And in the numerator of this equation, we have K that stands for permeability of the reservoir. H is the thickness of the reservoir, and P bar, which is average pressure or average reservoir pressure. These variables we can control. And in the denominator, in the red actually square, we have oil formation factor, which is P sub O, and viscosity of oil. Again, this is given by nature and controlled by nature. While engineers can play actually with some other variables in these equations, like the BWF, which is the pressure at the bottom hole of a flowing well, and the radius, the drainage radius, and RW, which is the well radius. This is something decided by engineers. And eventually the last variable, which is S. S stands for the skin. And the skin is the damage introduced by different mechanisms. So we will come back to this equation later. Now there are different types of formation damage. So formation damage can be driven by different mechanisms, like, for example, mechanical, biological, thermal, chemical mechanisms. Mechanical and chemical mechanisms contribute to lots of formation damage because of their nature. So, for example, if you look at these red square or rectangles, when it comes to mechanicals, we always talk about phase trapping or fine migration, solid invasions, mechanical damage, friction-induced damage, and so on. Chemical damages, basically, they are related to interaction between fluid and fluid, interaction between fluid and rock, interaction, let's say, related to wettability, whether the rock is oil wet or water wet in here. So these are the types of damages that occur, because we always drill. When we drill, we use different fluids for drilling. The fluid could be water-based, could be diesel-based. So imagine drilling a formation that is, let's say, oil wet. It loves oil. Then diesel will penetrate further, carrying out the species of drilling mud, and formation damage will be enhanced in this case. So, can we control formation damage? can we remove it, and how can we remediate this one? Actually, as shown in the animation videos, formation damage penetrates so deep, and of course, if we leave it as a function of time, or if there is an ideal time of drilling, this will take the process further, okay? So we can remove it by the so-called stimulation. We can use acids to clean up the lower part, or let's say the part to be completed for production. But the stimulation does not always reach, you know, the area that was damaged by drilling. So formation damage in general is an irreversible process. So what goes into the reservoir does not necessarily come back. And actually by Porter, a scientist, he said it's exactly similar to reverse funnel phenomena. You know, the reverse funnel shown in here, basically if it is in the right position, okay, you can pour the water into the funnel and all the water goes through. And this is the case when we drill. So basically the fluid goes into the reservoir. Now back from the reservoir, because of the capillary effects, not all the fluids, they come back. So you try just to pour the same amount through this smaller diameter, and definitely there is no way to bring it back. So to conclude, then we have to prevent actually formation damage instead of fixing the delicate formation, especially when we talk about shale or tight gas. So we better prevent formation damage ahead of time. Well, how can we do that? How can we prevent the damage before it happens? Then we have to find, basically we know the problem, okay, and we need to remove it by putting a solution in place. And one way actually to do that is by drilling or by controlling the pressure while we drill. How can we do that? This is always done by surface companies. And the pioneer in this field used to be Weatherford, because they had a company called Precision Drilling, specialized mainly in drilling. And there are 3 types of drillings to manage the pressure, okay? Because as you saw, the damage is caused because of overbalance, because of high weight of hydrostatic pressure, along with other factors in the formation. So one way is using the so-called managed pressure drilling, and this one we optimize the drilling process itself. And when we use managed pressure drilling, our intention is not to invite reservoir fluid to flow, okay? While the other 2 types, underbalanced drilling and air drilling, are used actually with an intention to produce while we drill. So we really care about inviting the reservoir fluid to the bottom hole, and then they go up to the surface. And of course, with underbalanced drilling, we can maximize reservoir values, as we're gonna see later. And with air drilling, used a lot if we drill gas reservoirs, we improve drilling economics. So in this lecture, we will just focus mainly in the middle one, which is underbalance. Now, underbalance, guys, it helps us a lot, not only during drilling process, but basically it has some phase later when we need to inject as well. So when the reservoir pressure goes down, and when the reservoir is called a depleted reservoir, then we can feel the effect of drilling underbalance because of having no damage. Underbalanced drilling is not a new technology. It wasn't introduced nowadays. Actually, the very first wells drilled used to be drilled underbalanced. And the only way for those drillers or for the rig people to know that they did hit a reservoir is by having a blowout when the oil and gas come out of the reservoir. And usually this is the only way to know, because at that time, if you look at 1850 to 1900, there were no good technology, and there was no other way but to have the fluid coming out of the surface. This was the only indicator that there is oil, and this used to be to call just oil out or flow out. Okay. Then, because of the safety reasons, many people passed away because of, you know, when the oil comes out or flows out, many people actually passed away, and then they said, well, there should be a way to control it, and they came with overbalanced drilling. So, and in the 50s, 1950s, air drilling was introduced actually to increase rate of penetration, so which means to drill faster. And in the 1990s, horizontal drilling, multilaterals, hydrofracking, all of these, you know, age of development in technology. Then in the 2000, actually, rebirth of underbalance came back, and again, now we don't worry about safety only, but we have to worry about the reservoir, okay? So we need to take care of our people, and we have to have our safe workplace, but in the same time, we have to take care of our reservoir from being damaged. This is just a picture of a spindle top discovery, where you can see basically a blowout, and this could continue for months or for a year or so. And again, this is a sign of having a well-drilled underbalance. This is other picture, actually. If you look at the right picture here, you see people, not only those who drilled the well, but you could find official people, they come to celebrate the findings. And if you look at the picture at the left, these guys in drilling rig, look at their safety equipments, happy at that time, hard workers, so basically to do the job. Now, when we drill underbalance, we have, again, I said we have to care about safety, and we have to control the well as well. So the well is controlled by three means: by hydrostatic pressures, by friction pressure, and by the surface choke. This is the one at the surface. Eventually, friction pressure, we don't control it much, is driven by the equipment. Surface choke, we control it, and hydrostatic pressure, we can control the weight of the drilling mud. Okay, we can lighten the drilling mud, or we can increase the density of the drilling mud. On top of this, we have to have a blowout preventer installed in order to provide a safe environment for work. So then what underbalanced drilling is? So underbalanced drilling is intentional reduction of the drilling fluid density. So we intentionally reduce the fluid density, which is the mud density, okay, to cause the hydrostatic pressure in the well, of course, lower than reservoir pressure, lower or equal, okay? So when we hit the reservoir, because the pressure at the bottom hole is almost a little bit lower than the reservoir pressure, then reservoir fluid will start to flow. And of course, this gave excellent effects for the case of horizontal wells. And a key factor, again, is formation damage minimization. There are some issues with pressure control in here. If the bottom hole pressure is reduced significantly, then there will be a large pressure drop between the reservoir, where you see the arrow down there, and the well. And this could result actually in the so-called a kick. So the kick happens in the reservoir area. If the kick is large, then the kick might be carried up to the surface and a blowout. So if the pressure is so high, okay, and we lose control over the drilling fluid, then this will take the rig away. If there is a source of, let's say, fire, of course, if the fire triangle is complete now, then of course we have oil and we have oxygen is there. If there is electricity or ignition point, then this will result in having a fire. And this is one example in here. I believe this is from Algeria as a consequence of drilling under balance without having well control. But we go back to the surface, okay? We always deal with the choke, okay, to control the pressure in addition to the blowout preventer. Look at this. This basically shows our underbalanced drilling mechanisms. As you can see now, when the drilling bit hits the top of the reservoir, and because of the difference in hydrostatic and reservoir pressure displaces the gas first into our product or in drilling well, and then the oil phase will start basically flowing along with the mud. They flow back to the surface. So in here, this is not a production, it's a drilling process where we have our hydrocarbon along with the drilling mud coming back to the surface. Now when we need to pull out of the hole, eventually we can pull out of the hole neatly. There is no damage whatsoever. Hydrocarbon flow eventually prevented mud cake layout, okay? So there is no mud cake, the hole is very neat. So, and the next step to be taken for completion, to complete the well, then the well can be completed right away with an open hole or cased hole. And there is no need to clean up or stimulate the well. The same phenomenon, my friends, can be observed in the horizontal well. If you look, when we penetrate eventually the reservoir, again, because of the differential pressure, so the oil will start to flow. And as we penetrate further into the formation or horizontal part of the reservoir, you can notice that this is animation. So the rate of flow does increase. And as we go deeper, because the rate of flow is not from the head part here, so from the vicinity of the drilling string, oil flows into the reservoir. Again, when we pull out of the horizontal section of this well, the hole is left very neat and ready actually for production. If this is highly consolidated, let's say sandstone where there is no need, okay, where there is no need to complete it, then it can be left without, let's say, completion or open hole completion. Two things to worry about in here. We need to worry about horizontal permeability when we drill horizontally, and vertical permeability. And usually, as you know, most of you know this, because of the overburden pressure, usually vertical permeability is less than horizontal permeability. So we have to take this into account when we drill, whether we drill horizontally or vertically or deviated wells as well. So when it comes to the applicability of underbalanced drilling, it's applicable when we have high skin, which is the S, if you remember, in the denominator of Darcy's equations. When S is really high, then we have to think of underbalanced drilling. If the rock formation is so hard, underbalanced drilling is basically a candidate among the drilling processes. Now, while we drill, we can characterize the reservoir. We can measure. We can do lots of measurement while we drill under balance. So some areas that might have lost circulations, okay, or let's say pressure depleted reservoirs are good candidates for underbalanced drilling. Sometimes some formations are really thin, could be 10 feet. Now, if drilled over balance, these space will be missed, and underbalanced drilling definitely sees them. And of course, there is other technology associated with underbalance. So we need to see our reservoir before we approach the top of the reservoir. different techniques exist. Okay, for example, we need to make, when we get closer to the reservoir, we can use gas chromatography, GC units, okay? And GC unit does make analysis, let's say from C1 to C6, along with some sour gases. And now we plot different ratios, and when these ratios basically cross or overcross, they tell us that we are almost 50 or 30 or 40 feet above the reservoir. So we get some guidance again by the use of technology in order not to miss. Now, if we are closer, let's say, to a thin layer, that's, let's say, 10 feet thin, so using underbalance and evaluating while we drill does not allow us to miss it. So we see it and we hit that reservoir. Where not to apply this technology if the formation is highly unconsolidated, soft formation. Soft formation, you know, you invite the flow, you invite lots of sands, and this is not a desired. Plastic flowing salts, if we have flowing salts, or tectonically unstable shale, if the shale is unstable. Now, the other issue, if the shale content, the clay content in shale is so high, let's say 40%, 50%, you have to take care of your base fluid, because if we use water, you know, clay does swell with water. So you make a damage, intentional damage to the formation. Now, which reservoir quality allows us to use underbalance? In here, there is a cutoff actually to consider when we look at the relationship between permeability and pressure. The red line or the red curve down there basically shows the border between underbalance and fracture stimulation requirement reservoirs. So if the reservoir requires fracture stimulation, then the basically values of permeability versus pressure is in this envelope. Now, above a green curve in here, so there is no need to use underbalance. So conventional completions is more economic than underbalance. So the envelope allocated for underbalance is in between these two lines. So this is basically what the investigation have shown or came up with based on screening. Now, what can we say about a reservoir that has a very poor quality? Does underbalance help us to enhance the quality of the reservoir? No. Underbalance is not a vaccine you inject into the reservoir to enhance its quality. So if the quality of the reservoir is really poor because of, let's say, sorting, because of compositions, because of type of the reservoir, because of having lots of isolated, let's say, pores, because of very low effective porosity, because of whatever reason, then underbalance is not a solution for this one. So poor reservoir stays poor reservoir. So how the technique is conducted? So in terms of the drilling, now I said, or I mentioned earlier that the mud, which is, let's say, water-based mud in here, you know, the density of mud is 1,000, okay, kilogram per meter cube. Now we can reduce the density of water, and of course we add some material to have the mud, bentonite, for example. So which gets, the density gets larger. To reduce the density in order to reduce the value of hydrostatic pressure, we inject gas, okay? We inject, for example, nitrogen, which is quite safe. And now, depending on the amount of gas, we lighten the fluid or we reduce the density of the injected fluid for the purpose of lifting, cutting, cooling the system, and different reasons, or cooling the pen. Now, these two fluids are mixed together in different ratios, and we control actually the gas to control the density, and at the end to control the hydrostatic pressure. When they reach actually the bottom area where we drill, where the cutting is coming, then the cutting along with the drilling fluid, they come back, and the main cuttings are taken over shaker, and the fluids go to a separator, okay, and they get separated. Water basically gets separated there, and some fluid goes into drilling fluid goes back for reuse, and oil is stored, okay. And of course, this is very initial treatment. And imagine if the well is a wild well, so basically we don't have proper surface facilities, but it has to be provided if we drill underbalanced. This puts basically an extra cost on the operator to pay to surface companies to drill the well underbalanced. Now we have everything back. We have cutting, water, we have oil, okay, and we produce, let's say, gas. Gas eventually can go to be flared or burned if a small amount of gas. Nowadays, they move to no flaring, no dumping into the atmosphere. The impact into the atmosphere has to be zero. Then the gas can be taken to treatment or to saline if it is methane, and so on. So what are the benefits of underbalance? So the benefits can be to different actually product lines or different components of petroleum industry. Benefits can be associated with the reservoir itself to increase net present value of the reservoir, for the drilling process itself, okay, for productivity index, to enhance productivity index. And of course, the most important one is to minimize formation damage. So when we minimize formation damage, we actually get added values to all other aspects of the reservoir. Another benefit, we access actually challenging reservoir, like the one we mentioned, 10 layers, let's say, depleted reservoirs. We improve reservoir characterizations because they are evaluated while we are drilling. We identified mist zones, already mentioned this one, increasing production and enhancing recovery, let's say at the later stage when the production declines significantly. Okay, again, we come back to this equation and how can we maximize production now? So this basically requires petroleum engineers to take care of the variables in green rectangular areas. So let's say the bottom hole pressure to be increased, not to deplete the reservoir, okay? So if you increase it, eventually the difference between reservoir and bottom hole will be what? If you decrease it, will be low, right? But now if you decrease it significantly, and the difference will be large, and when you multiply the pressure drop by the factor related to permeability and thickness, then the numerator value will be quite high. But the most important one to worry about in this equation is skin factor in the denominator. RW, we can control it. We can basically set the bottom hole area or the well radius in the bottom hole. Well, how does skin, which is S, affects production? As you can see in this figure in here, in y-axis we have production in barrels of oils per day. It goes up to 1,000. And in x-axis, we have skin, which is S. So skin can be negative, can be positive. As you can see, when the skin is positive, so basically it adds to the denominator, and the production is reduced almost to 200. When a skin is negative, let's say -3, the production is almost basically 10, maybe 5 folds or 4.5 folds larger than when the skin is 15. And this is the main driving force in here, to minimize the skin, to prevent damage from occurring, okay? We don't need to go to stimulation or to treatment if we can avoid this one by utilizing a good technology. Other reason, guys, why Underbalance is good to use, because it does increase the drainage area. Now in here, what you see 2 wells, okay? So the well in the left and well in the right, and there is a distance between them, okay? And if you look at this is a pressure distribution here. If you look at the pressure distribution, there is a significant actually a drop, okay, in the vicinity of the well and in both sides, where the drainage area shared between these 2 wells is equally divided. Now let's say if we drill the well at left side, if we drill it under balance, we will get rid of this one, the pressure drop due to skin. There will be no pressure drop due to skin, and eventually the drainage area will be enlarged. So now the well at the left side will produce oil from further area. So basically is approaching the well at the right side. And this basically we don't see. It happens down there in the reservoir, but it can be felt by the amount of production and other factors as we see. Now we can preserve reservoir energy, okay? So when we drill under balance, this is at a later stage, not during drilling. And of course in here, if there is no damage done, let's say to water drive mechanisms while we drill, okay? So because this is one of the mechanisms that results in the highest recovery when oil is displaced by water. Let's say if no damage is done in the gas cap in the upper part of the reservoir, okay, gas cap area, then gas cap gets expanded, and later on when the reservoir pressure goes down, so the gas cap gets expanded, gets larger, and definitely will contribute to production. Or solution gas drives, okay? Solution gas, when the pressure in the reservoir goes below bubble point pressure, so we start producing gas from the reservoir itself. So gas will come from all part of the, let's say, bottom hole. So, and this basically value is paid off later. Now, let's say after many years of production, a company decided to abandon a well for a reason or another. So what is the effect of underbalance, or let's say formation damage on well abandonment? So these are 2 wells in here. You see the well at the left, basically we see pressure versus distance into reservoir. And that's what we care about, okay, how deep we can go into the reservoir. So pressure versus reservoir, this is for damaged well that was drilled over balance. And as you can see, the pressure is quite high. Now, and we have a pressure due to skin or pressure drop due to skin in the vicinity of the well. In the right-hand side, we have undamaged well, which is drilled under balance. And you can see the pressure profile is shifted down. Now, if we decide, let's say, basically to abandon the well, what can happen? The well that was drilled under balance can be abandoned at lower pressure. What does this mean? This means we can prolong the life of our well for longer time. So let's say instead of having this well in operation for 20 years, okay, then this well can produce for maybe 30 years, okay? So, and this is an unseen actually effect. The other one, we can increase the recovery 2 ways. whether we produce under natural behavior of the reservoir, or we use, let's say, secondary and tertiary methods. Now, in this figure, we see in y-axis the production, and we see the dashed line, which is economic limit. We cannot go above this economic limit, okay, of production. And we see two curves, one for the damaged well over balance, it's in black, and the other curve for underbalance or undamaged well. For the same economic level, actually, one can observe that the undamaged well results in higher rate of cumulative production. So we produce more, although we use the same economic limits for the two wells. What should we take away actually from this talk, my friends? We should always remember that underbalanced drilling is not a solution for poor reservoir qualities. And of course, we maximize, or by the utilization of underbalanced drilling, we maximize what's given by Mother Nature. Okay, so we can't change what's given by Mother Nature in terms of properties, but we can maximize our production of oil and gas. But how to do or when to drill under balance, there is no way to go ahead and drill under balance unless we make a candidate screening. So there is a procedure to follow to look, because not every reservoir is a candidate for under balance. So we have to make some screening and some calculation, and then come up with different scenarios and probabilities is there to decide whether to drill under balance or not. So by doing so, I wrapped up my lecture, and I'll be more than happy to answer any question. Thank you so much.
Thank you, Dr. Abdelaziz, for sharing so much of that information with us. That was really comprehensive. Those of you who have questions, you can directly ask Dr. Abdelaziz.
Any question, my friends in Saudi? I know that you had a long day, and having such a lecture at the end of the day is a bit tough, right? Anyway, in the last slide, I have my email. In case if you don't have any question, just you can drop me an email. I'll be more than happy to respond if you don't have any question.
Well, okay. Thank you so much, everyone, for participating in this lecture today. If you have additional questions, you can contact Dr. Abdelaziz, or you can contact us at our SPE chapter. Again, thank you, Dr. Abdelaziz, for your time and for providing such valuable information for everyone. We really appreciate it. Have a great evening, everyone, and goodbye.
I have a question, Doctor, if I may.
Okay, this is good. Go ahead.
Thank you very much for the great presentation. You mentioned one thing about depleted reservoirs.
Yes.
We can drill with underbalanced drilling technology, depleted reservoirs. What about wellbore stability pressure? Does it have to be like, you know, the less than the pore pressure?
Well, this is another issue.
I know, yeah, just for depleted reservoirs. I mean, yes. we all know for underbalanced drilling, you should have a wellbore stability pressure less than pore pressure.
Yes.
But
yes.
For depleted reservoirs, does this rule apply to this, this technique?
Well, actually, depleted reservoir in here, when you talk about low reservoir pressure, okay? Now, you know, when you drill over balance, if the reservoir pressure is really low, the damage is significant. Now, when you drill under balance, eventually you can move to air, almost completely air, mud, okay? And drilling, basically, mud weight is so low. And in this case, you cannot introduce, a large damage to the reservoir. And you still need to make assessment actually or to make screening for such a depleted reservoir, whether it can be really drilled under balance or not. So you have to gather all the info and go through a candidate screening procedure. There are different softwares used for this one. You look at the formation itself, whether it is clastic or carbonates, whether it is, let's say, a poor formation or poor reservoir. So as I said, it's underbalanced drilling is not a solution for a poor reservoir. Some depleted reservoirs are already poor reservoir, considered to be poor.
Thank you very much.
You're welcome. Any other question?
Yeah, I have a question. Good afternoon, Dr. Abdelaziz. My question is like, you mentioned like underbalanced drillings, like reducing the what's called formation damage. But I think the underbalanced drilling is firstly is expensive. It costs a lot of money, and it's, it's a risky. As you mentioned in the presentation, it costs a kick. Like during the production, if the like formation damage happened, we have a lot of the method that we can use it, like hydraulic fracture or acidization to reduce the formation damage. So it's not better like using those process, like if you compare to like the underbalanced drilling. Well, it's underbalanced is more costly and it's very dangerous. Like maybe it's cause kick and the blowout, stuff like that.
Well, I agree with you to some extent. The cost is higher because of the processes associated with underbalance if you evaluate while you drill. But as I said, okay, in underbalance, we have to worry about safety as well. And safety is taken care of in terms of blowout preventers, choke. And of course, we need to make near real-time actually analysis for what comes out of the reservoir in order to be aware before we hit the top layer of the reservoir that in our way there is a reservoir. And the rig crew have to be ready, okay, that we are approaching the reservoir and we have to be prepared for any possible kick. And sometimes you get small kick, and as you penetrate further, you get a larger kick that might result in a blowout. But nowadays, with the blowout preventer, this basically is minimized, or it does not exist such type of problems. So you hear of it very rarely that where you have a blowout, okay? And these mistakes mainly are done by humans. If you observe the technology very well, definitely you can minimize the kicks. Now, when it comes to stimulation, you mentioned that with overbalance, you can use hydrofracking and you can use stimulation. Yes, stimulation is done after drilling overbalance to clean up the mess actually in the bottom hole area, but it does not do the job perfectly, as you noticed in the animation when the underbalance is basically carried out. The bottom hole area is neat and clean. There is no mess. There is no basically the cake is not or the mud cake is not laid off in that area. Now, hydrofracking is completely another job. It has nothing to do with drilling. It comes later.
I know it's in production. Yeah, yes. When the formation damage.
Yes, it comes. But again, in hydrofracking, you induce lots of formation damage. Okay, yeah. Maybe that's the thing you wanted to introduce. But we do hydrofracking, for those who don't know, to make opening in the formation to increase the surface area available for flow and to increase the permeability of our reservoir. And this is usually utilized in or nowadays is utilized with unconventional reservoirs such as shale gas, tight gas, and others.
Yeah. Thank you, Dr. Abdelaziz.
You're welcome.
Thank you, Dr. Abdelaziz, for your great presentation. It was really useful. Also, I have a question, please. Like for this underbalanced method, can we use it everywhere, like offshore, onshore, or like in every places? For example, some places are shale, like others are different. Like, is there any way to like know which place is better to use underbalanced?
This is a good question, Sardam. Thank you so much. Actually, you can use it as long as the screening tells you that, okay? But when it comes to offshore, we always have problem with the footprint because eventually underbalance requires some footprints, okay? You need to have some facilities in the surface ready to deal with the produced oil and gas, okay? Now, when you do underbalance or when you do overbalance, eventually there might be no issue because we hit the reservoir, we don't produce right away, or we shut in the well. But with overbalance, with underbalance, because of the simultaneous production while we drill, we have to be ready for this. So this is an issue or another issue that we have to take care of when it comes to offshore. Because, you know, offshore, we always take care of available space. It's very limited space. Even when it comes to separators, we have no issue, let's say, if we drill inshore to use horizontal separator. While if we drill offshore, we have to convert or to move to vertical separators instead. So many issues has to be considered when the process is decided, but it can be applied in both offshore and inshore. But the cost definitely will be driven up, okay, when you move to offshore.
Thank you so much, sir.
You're welcome.
Persha's PC is like, she cannot join because of low power. So any more questions, please? If not, we can end the lecture.
Thank you so much. Thank you so much, Sardam. Thank you so much, everyone. I really appreciate your presence, and stay safe, please. Thank you so much.
Thank you so much, Dr. Abdelaziz. It was a pleasure to have you as our lecturer for today. Thank you very much, everyone, for participating in this lecture.
Thank you.
And take care.
You too. Bye-bye.
Bye-bye.